Hey everyone, welcome back. In this video, we're going to be covering sedimentary rocks in detail. Now, remember that metamorphic rocks, igneous rocks, and sedimentary rocks can all be turned into sedimentary rocks, and that involves a number of different processes, including erosion and weathering, which we talked about in a previous video, but also transportation, deposition, and lithification. We're going to talk about all of these processes in this video in detail. So we're going to be covering what sedimentary rocks are, again, those steps in the formation of sedimentary rocks, and then we're going to cover two major categories of sedimentary rocks that include clastic and chemical sedimentary rocks. So what is a sedimentary rock exactly? Sedimentary rocks typically form near Earth's surface. They are formed from sediment, including any pre-existing rock or mineral class or minerals precipitated from solution, as well as skeletons or organic material. So we talked about this in the video where we covered weathering and erosion. And there are two main types of sedimentary rocks. There are clastic sedimentary rocks, which you can imagine they're made up of clasts of rock or mineral. And then there are chemical sedimentary rocks, which are a little bit more complicated and are a lot more variable. There's some really nice pictures here to give you an idea of what sedimentary rocks look like out in the wild. This picture on the left here is in Arizona. This is a famous place for photographers to go called The Wave. And it's really beautiful, and you can see some really excellent sedimentary structures here, including bedding and cross bedding, which we'll get into in another video, but just sort of teasing a future lesson. And you can also see variations in the composition of this sandstone. You can see that some layers are more oxidized than others. You have sort of the light tan layers, which are less oxidized, and the red layers, which are more oxidized. And then there's an image here of a famous hike in Zion National Park called the Narrows, which is this awesome opportunity for you to hike through a slot canyon that has the Virgin River going through it. And there are a lot of important sedimentary processes going on in this one location, including weathering and erosion. Those are taking place actively. You're also getting transportation of clasts by the river itself. So that river is carrying large clasts of rock down the river, and it's transporting ions as well. And we're going to talk about how all of those processes are important to the formation of sedimentary rocks. All right, let's talk a little bit about what it takes to form a sedimentary rock. There are about 5 steps involved, including weathering and erosion, which we covered in detail in a previous lesson. Then there's transportation, deposition, and lithification. You can see in this diagram here, we have weathering of this cliff face here, erosion, those clasts are falling from the side of the cliff face down to the bottom, and perhaps they're getting picked up and transported by this river. The river is probably transporting solid particles as well as ions that are being dissolved in the water, and those are being deposited all along the way and also at the beach and into the ocean. Or maybe this is a lake. Hard to tell. And then after those sediments are deposited, they become lithified, and the process of lithification involves compaction and cementation. So transportation is really the process of moving, just like it sounds, moving clasts or ions from one place to another. Remember that sediment can involve dissolved ions. So I like to think about salt, for example. When you put salt into water, it dissolves into sodium and chlorine, and those two ions are just suspended in the water, and they are moving along until they have to precipitate out of the water. So salt is a really great example, and we're going to talk about how that then becomes rock later on. Those clasts and dissolved ions are being transported by a transporting medium. So that's primarily water, wind, and ice. And they all have different abilities to carry sediment. They don't all carry sediment in the same way, and they don't all deposit sediment in the same way. So wind, as you can imagine, picks up clasts, suspends them in the air, and then drops them rather quickly. Water can carry particles for a really long way, and can also carry those ions dissolved in the water. Ice can also pick up clasts and carry them for quite a long way and then eventually drop them when the ice melts. The ability of that transporting medium to carry those sediments really depends on the viscosity and the velocity of that medium. Viscosity being the material's resistance to flow, so something that's really viscous is really resistant to flow. Something like honey or molasses, if you're familiar with the phrase "slow as molasses." So that's a very viscous material. And then velocity is sort of the speed at which that medium is transporting material. So in terms of transportation, we're talking about a few different methods of transportation, including suspension, so having something actually suspended in that transporting medium and being moved along. You can also have saltation, which is those particles bouncing along the bottom of that transporting medium. You can have traction, where you have the sediments sort of being dragged along the bottom, as well as bed load clasts, which are really just settled at the bottom. All right, let's talk about deposition. So deposition is the process of sediment actually settling out of the transporting medium. And this occurs when there's a decrease in velocity, or if we're talking about glaciers or ice, we're talking about when the ice melts. So that's when deposition occurs. There are a number of what we call depositional environments. These are the environments in which deposition tends to take place. And in each of these environments, you'll find unique sedimentary rocks. So a few very common ones that we'll talk about are glacial environments, alluvial environments, aeolian, where you find sand dunes. Fluvial refers to streams and rivers. Lacustrine is another word for lake environments. We have evaporitic, tidal, shelf, continental margin, slope, abyssal plain, reef, lagoonal, deltaic. These are all different environments where you expect deposition to occur. And places, these are environments that you can actually observe in the geologic record. So I could walk up to a rock today and judging by its characteristics, I could tell you what type of environment it formed in, which is pretty cool. All right, let's move on to lithification. So once the sediment has dropped out of the transporting medium, it goes through a process of lithification, or becoming rock. The prefix there, lith, actually means rock. So if you see lith anywhere, that refers to rock, just for future reference. Lithification really involves sort of two steps. Compaction, or sort of the removal of pore space. This is the process of overlying material accumulating and then pressing down on clasts and packing them together more tightly. And then there's cementation, and that's when you get minerals like quartz or calcite precipitating out of water and filling the spaces, the remaining spaces between clasts. And this process can occur over a long period of time, and it's definitely not instant. It takes a long time for lithification to occur. But just keep in mind, lithification it's this two-step process that these things are kind of happening simultaneously. You have compaction and cementation. Okay, let's talk about the major categories of sedimentary rocks. In this course, I like to divide sedimentary rocks into two major categories. But if you're, say, enrolled in the lab portion of this class, they might have more categories of sedimentary rocks. So just make sure that you're working with your lab instructor to make sure that you know what categories they're looking for when classifying sedimentary rocks. But in this class, I really just cover two major categories, the first one being clastic sedimentary rocks. And just like it sounds, clastic sedimentary rocks are made of clasts of either other rock or mineral fragments. And the word clastic comes from the Greek word klastos, which just means broken. So broken fragments from previous existing rocks or minerals. These are also often referred to as detrital sedimentary rocks. So don't get thrown off if you hear the word detrital, or detritus is another word for sediment or clasts. So that's another synonym for clastic sedimentary rocks. So when we're classifying clastic sedimentary rocks, there are a few things that you want to consider. One characteristic of the rocks that's really key to classifying them is the grain size. So how large those clasts actually are. And there is a very frequently used grain size scale called a Uden-Wentworth grain size scale. And this is a tool that a geologist might carry in their pocket while they're out doing geology and observing rocks. They might carry a card sort of similar to this one here on the screen. That it's a reference card. It lays out what different sand sizes are called. You have very fine, medium, coarse. And it's really just a reference to be able to describe the size of the grains within the rock. Just for reference, the Uden-Wentworth grain size scale uses millimeters and microns or micrometers. And a micron, if you aren't familiar with it, is a millionth of a meter. So maybe you can kind of imagine what a meter looks like. A micron is a millionth of that, or a micron is 1/1000th of a millimeter. So if I'm looking at my ruler again, you might want to grab yours just so you can get sort of a visual idea of what a micron is. You want to look and see if you can identify a millimeter on your ruler. Okay, I found a millimeter, so it's 1/10 of a centimeter, and a micron is 1/1000th of that. So you can't see it. You definitely need some high-powered equipment to observe a single micron, but just so you know, a micron is extremely small. But those are the units that the Uden-Wentworth grain size scale uses. So you want to sort of become familiar with the metric scale in terms of microns and millimeters. We also think about sphericity. So sphericity is the degree to which clasts have the same dimensions in all directions. Something that is oblong is not spherical. It's sort of a stretched out sphere. But if all of its measurements in every direction is sort of the same, that would be something that's spherical. An egg, for example, is not very spherical. It's kind of a stretched out sphere. And the reason we think about these things is because as sediments are transported, they become more rounded and smoother the further that they travel. So something that is very close to its source or very close to where it eroded down from would be very angular, like the rock you see here on the left. So that would be considered a breccia. Something with really angular clasts would be a breccia. And then clasts that are really well-rounded and very spherical would be considered a conglomerate. So that's sort of a major difference between those two similar but different rock types. When we're classifying clastic sedimentary rocks, we also want to think about what we call sorting, and that is the degree to which clasts of rock are the same size. So a rock can be very poorly sorted if it has a mix of really large clasts and really small clasts. That would be considered something very poorly sorted, and something in which all of the clasts are sort of the same size would be considered very well sorted. It's important to note here that if a rock is very poorly sorted, it has, say, cobbles surrounded by sand, then those smaller grains are considered what we call the matrix. So that's a word that you might hear pretty frequently. When we're classifying sedimentary rocks, we also want to consider what geologists call maturity. Maturity is the degree to which a rock or a sediment has evolved from its source rock. So if something is really well-rounded, well-sorted, and consists only of its most resistant minerals, then it would be considered a very mature rock. Quartz, for example, is very resistant to weathering, and in a mature rock, usually quartz is one of the last minerals present. So that is a good indicator of maturity. In an immature sedimentary rock, you might find quartz as well as lithic clasts, feldspar, and other minerals present. So that's a pretty good indicator of a rock that's not very mature. It's also really important to describe the composition of any rock that you're working with, including sedimentary rocks. You want to describe whether they are pieces of minerals, and if they are, what kind of minerals are they pieces of? Or are they pieces of rocks, or what we call lithic clasts? And if so, what kind of rock? Are you able to identify that pre-existing rock? Or are there fossils? Are there shells? These are all things that you want to consider when you're describing a clastic sedimentary rock. For example, if you have a conglomerate or a breccia where the clasts are relatively large, they're cobble or boulder-sized clasts, then you can probably clearly identify what the clasts are made out of. You may be able to say that clast is a quartzite, that clast is a granite. So being able to identify rocks within rocks is a very important part to describing clastic sedimentary rocks. Let's talk about classifying sandstone in particular. So according to the Uden-Wentworth grain size scale, there is a size that is specifically called sand, and rocks that have sand-sized particles are called sandstones. And because sandstones are so common, it's such a common grain size, it's important to further describe what the sandstone is made out of, because chances are it's not just quartz sandstone. So there are sort of 3 general categories of sandstone that you might come across. Of course, geologists can always get more specific, but these are the 3 general types of sandstone that you'll see. A quartz arenite sandstone, for example, is made up of more than 90% quartz. These rock types make up a very small portion of the world's sandstones, but they do exist. There are quartz aranite sandstones out there. But most of the time, your sandstone is going to have other clasts within it. So for example, you might have an arcosic aranite sandstone, and that's a sandstone that has more than 10% feldspar making up that rock. Or you might have a lithic aranite sandstone, which is more than 10% rock fragments. Remember, lithic refers to fragments of pre-existing rock. When we're talking about classifying clastic sedimentary rocks, it's also very important to describe the cement or the matrix. So if your rock has cement between the grains, they don't always have a visible cement. And if you're able to describe that cement, you definitely should. Most often, cement is made out of quartz or calcite. Those are by far the most common types of cement that you'll see. And obviously, if you put hydrochloric acid on the rock and it fizzes, there's a chance that a component of that rock is calcite. A sedimentary rock can also be what we call matrix supported. So I mentioned this before. If you have a rock that has clastic sedimentary rock that has very large clasts surrounded by smaller clasts, so smaller clasts are considered what we call the matrix. And it's really important to be able to describe the matrix if you can, if the particles are large enough for you to describe and determine the composition of. Okay, so let's move on to talk about the second category of sedimentary rocks, and those are chemical sedimentary rocks. Chemical sedimentary rocks are primarily made out of ions that have been transported through solution, like we've talked about in the past. So again, if you were to put salt, say, in water, it would dissolve into sodium and chlorine, and those would be suspended in the water until they precipitate out. They're really, like I've alluded to, there really isn't a perfect divide between clastic and chemical sedimentary rocks. That division is pretty blurry because clastic rocks often contain some sort of chemical component. Maybe they have a cement, that would be a chemical component. Or, chemical rocks often contain clasts. So you might have a limestone that has some mud or sand in it. That happens all the time. So again, that division between the two really isn't that clear, but we do our best as humans to describe the natural world around us as best we can. So let's talk about some common types of chemical sedimentary rock. A few of these are words that you're going to come across over and over again that you've probably heard in your daily life already. And that includes limestone, very common rock. It is the most common chemical sedimentary rock out there. Chert, banded iron formation, or BIF, and evaporites. So we will talk about each of these individually. So limestone, again, this is the most common chemical sedimentary rock, and it forms in a couple of different ways, but most commonly it forms in oceans and on shallow continental shelves. That's sort of its primary formation or depositional environment. It really likes warm tropical regions with coral reefs. That's a very, very common place for limestone to form. And again, when we find rocks like limestone, that tells us something about the depositional environment. So if we find a limestone, we might start thinking, I wonder if this used to be a coral reef or a shallow continental shelf. Those are the things that should start going through your head when you come across a limestone in situ or out in the field. Some limestones tend to form in deeper water, and they can form from carbonate shells from plankton and things like that settling on the bottom of the seafloor. But it's really important to note that calcite dissolves back into the water below 4,000 meters. So at a certain point, there's too much pressure on the calcite for it to stay in solid form. It actually, the pressure forces it to go back into solution. So again, think about your Coke bottle, right? So remember we used the Coke bottle analogy when we were talking about dissolving volatiles in solution, so forcing those gases to be a part of the liquid. The same thing is sort of happening here with calcite. You're putting the calcite under so much pressure that it actually dissolves into the ocean water below 4,000 meters. So at that depth, you actually won't see calcite precipitating out of the water. It is dissolved in the water. So you won't actually see limestone that formed at depths below that point. A few other ways that limestone form, but these are far less common, although they're really interesting, include tufa towers. So if you were to go a little hop, skip, and a jump over the Sierra Nevada from Sierra College, you would find yourself near Mono Lake, and maybe you've been there before. But Mono Lake is a really neat place because we have evaporation going on, and that evaporation is causing the precipitation of limestone to form these towers. And what's really happening here is when you have the water evaporating away, that limestone can't be in solution anymore, so it has to precipitate out. We also get limestone forming as travertine in hot springs, and this is sort of a less porous form of tufa. Tufa is pretty porous, but travertine is the type of limestone that forms in hot springs. And then we also have a form of limestone. These forms are called speleothems. I bet you've never heard that word before, but you can use that as your next party trick. Stalactites and stalagmites are holistically referred to as speleothems in the geologic community, and those form in caves. So you've probably, or maybe you've been on a cave tour at some point in your life, and you've seen stalactites and stalagmites. So and that's from water, again, sort of dripping down from the ceiling of caves, and limestone being precipitated out of that water. Let's talk about a rock type, a chemical sedimentary rock called chert now. So chert is a really interesting type of rock that has the same chemical composition as silica, or quartz, hydrated quartz. So just like we had limestone forming at the bottom of the ocean from plankton that have calcium carbonate or calcite shells or skeletons, there are also some living creatures in the ocean that have bodies made out of silica or hydrated quartz. Two types of these include radiolaria or radiolarian, and diatoms. These are both creatures that have silica bodies, and when they die, those skeletons get deposited on the bottom of the seafloor and they accumulate as what we call chert. Flint, for example, is a form of chert. So you might use flint to start a fire. that's forming from these what we call microcrystalline quartz. So very small little bits of quartz that are collecting on the seafloor. Oftentimes you actually find chert and limestone, what we call interbedded. So you'll find alternating layers of chert and limestone. Just as sort of an aside, you or maybe your parents or someone you know might have used what we call diatomaceous earth as a way to get rid of pests in your house. Diatomaceous earth is made out of diatom, so it's made out of these little silica skeletons, and what it does is it dehydrates pests in your house and they die. So that is your cool fun fact that you can take into your everyday life. All right, the next chemical sedimentary rock that we're going to talk about is banded iron formation, or just for short, we call it BIF. These are formed in the deep sea floor, and they are alternating layers of iron oxide and iron poor chert, like we just talked about. So BIF in particular is sort of these alternating layers of iron oxide and chert. BIF is extremely prevalent in rocks that are pretty old, so almost all of the BIFs on Earth are Precambrian in age. So they're about 2.4 billion to 1.8 billion years old. They're very old in terms of the rocks that we have on Earth. And if you were wanting to go find BIFs in North America, you would want to go to the Midwest, where we have the North American craton. The North American craton is the oldest, most stable part of our continent. And that is in Minnesota and Wisconsin and Michigan and Canada. So that's a very stable part of the North American continent, and that's where you could go to find these old Precambrian rocks called BIFs. These are really the result of changes going on in the atmosphere at the time of these rocks being deposited. So changes in the atmosphere as well as the ocean. You might recall back to our discussion about the formation of Earth, and how we know how old the Earth is and things like that. We did actually mention BIFs back in that lesson, and they're formed by oxygen-producing photosynthetic cyanobacteria. So the cyanobacteria were the first things to produce oxygen in our atmosphere. That's where our atmospheric oxygen came from originally. And that change of producing oxygen reacted with the iron in the oceans, and it caused the iron to settle down at the bottom and form these banded iron formations. Banded iron formations are also very frequently mined. They form what we call iron ore, which is economically viable rock, a rock that you would want to mine, a rock that has enough of the component that you're needing to extract out of it, like iron, in order for it to be profitable. So BIFs form a lot of our iron ore in North America. Okay, I just want to add very quickly that although in this class we divide our sedimentary rocks into clastic and chemical, you might come across the word biochemical, and that is just a word for chemical sedimentary rocks that are formed from previously living things. So coquina is a rock that's made out of pretty much entirely shell fragments. Chalk is made out of the coccolithophores, or the limestone producing plankton. There's limestone mud, diatomite, and chert. Those are all biochemical sedimentary rocks. Okay, so with that, we have covered quite a range of the sedimentary rock scope. We talked about what sedimentary rocks are and sort of the process of formation from weathering all the way to lithification. And then we talked about clastic sedimentary rocks versus chemical sedimentary rocks. And I hope that that was a clear distinction between the two. Again, check with your lab instructor to see if they divide those up into further categories. I hope you got something interesting out of this. If anything, maybe you learned that diatomaceous earth is made out of diatoms, and that's pretty cool. But anyway, I hope it was a helpful video, and I'll see you next time.